Its impact was immediate, with airlines reporting higher passenger numbers and smoother operations, transforming air travel from a luxury for the elite into a practical means of transportation for the growing middle class. Air warfare was evolving simultaneously, but the advances in commercial aviation were no less remarkable. Designers were pushing boundaries, combining aerodynamic efficiency with mechanical reliability, striving to build planes that could fly farther, carry more weight, and operate in conditions previously thought impossible. Before the United States had even entered World War II, the race for faster, larger, and more capable aircraft was on, not just among military contractors, but in the commercial sector, where the stakes involved both innovation and profit. The concept of a four-engine airliner was not merely a technical challenge, it was a statement of ambition. Airlines wanted planes that could traverse the continent without stopping, offering passengers a new kind of travel experience, a smooth ride, spacious seating, and the ability to maintain schedules regardless of distance. The DC-3 had shown that a well-designed aircraft could reliably connect cities, but the dream now was larger. Engineers at Douglas began imagining a plane that could carry twice the passengers, cover distances that had previously required multiple stops, and do so with an elegance that seemed almost futuristic. This was the birth of the DC-4, a plane that would become an icon of American aviation and a symbol of technological prowess. Around this time, the pressures on engineers were immense. Airlines were demanding rapid development cycles, and manufacturing processes were still catching up to the complexity of new designs. Each innovation had to be tested, measured, and refined. Material science, aerodynamics, and engine performance were all advancing in parallel, and a miscalculation in any one area could compromise the entire aircraft. The Douglas teams worked tirelessly, iterating on prototypes, refining wing shapes, adjusting engine mounts, and perfecting fuselage aerodynamics. The design process was painstaking, combining empirical testing with theoretical calculations in a way that few other industries required at the time. But innovation in the 1930s was not only about engineering. It was also about perception. Airlines sought to brand themselves as modern, sophisticated, and reliable. A new aircraft was a marketing tool as much as a technical achievement. Passengers wanted comfort, but they also wanted the confidence that the plane could make the journey safely. The DC-3 had achieved this balance, earning a reputation for robustness and reliability that became legendary. For Douglas and its competitors, the DC-4 represented the next step, a plane that was not just functional, but aspirational, promising both speed and luxury in equal measure. Before the Second World War, American engineers did not fully realize how closely their innovations would be observed overseas. Across the Pacific, Japan had its eyes firmly fixed on the United States. Japanese military and industrial planners understood that the future of aviation would determine the outcome of global conflicts and national power. They were particularly interested in American advancements because the United States combined both industrial capacity and innovative design in a way that Japan could not yet match. From long-range airliners to high-performance military aircraft, every breakthrough in the United States was carefully studied, documented, and analyzed. The DC-4, which would eventually replace the DC-3 in commercial service, represented a leap in both technology and ambition. It was a four-engine aircraft capable of carrying passengers over long distances without refueling. Its design incorporated the latest in aerodynamics, weight distribution, and engine reliability. Pilots found it responsive, engineers found it efficient, and passengers found it comfortable. It was more than an aircraft. It was a blueprint for the future of both commercial and military aviation. The temptation for foreign powers to study, imitate, or even reverse engineer such a machine was immense. As America expanded its aviation capabilities, the allure of these innovations crossed the ocean. The story of the DC-4 is not just a story of engineering excellence. It is also a story of ambition and observation. Airlines wanted to transport people efficiently. Engineers wanted to push the limits of what was possible. And abroad, other nations watched closely, eager to learn, copy, and potentially exploit the advancements that had been achieved through years of experimentation, testing, and refinement. In this period, the stage was set for a collision of ingenuity and espionage, a historical episode that would later reveal the perils of attempting to replicate brilliance without fully understanding it. The birth of innovation in American aviation was, therefore, more than the creation of an aircraft. It was the emergence of a standard, a benchmark, and a symbol of what industrial ambition could achieve. From the first DC-3 to the emerging DC-4, every rivet, every engine adjustment, and every aerodynamic tweak represented countless hours of human effort, trial and error, and intellectual daring. And while Douglas Aircraft focused on pushing the boundaries of what was possible, far away in Japan, the eyes of engineers and military planners were fixed on understanding, and perhaps one day mastering, these marvels of American ingenuity. The world of aviation was becoming a stage on which innovation and ambition, observation and imitation, would collide in ways that neither side could fully anticipate. In the late 1930s, while American aviation soared to new heights, thousands of miles away in Japan, a different kind of air race was underway. Japanese military planners and engineers were watching the United States with intense scrutiny, fascinated by the breakthroughs achieved by Douglas Aircraft and other American manufacturers. Japan had ambitions that extended far beyond commercial aviation. The military sought planes capable of projecting power across the vast Pacific, yet domestic designs were limited by industrial capacity and technical expertise. The success of American airliners, especially the DC-3 and the emerging DC-4, represented both inspiration and a challenge. How could Japan match such technological sophistication when the aircraft were products of decades of research, testing, and incremental innovation? Before Japan could even begin its own long-range aircraft program, it needed a direct model to study. In a daring move, the Japanese government purchased an American airliner through intermediary companies and private agents. The plane was shipped to Japan, ostensibly for commercial use, but its arrival marked the start of a secretive and ambitious project. Japanese engineers dismantled the aircraft piece by piece, documenting every rivet, bolt, and system in meticulous detail. They measured fuselage dimensions, examined wing curvature, analyzed engine components, and studied the electrical systems that powered instruments and controls. The process was exhaustive, reflecting both their determination and the inherent difficulty of replicating technology that had been developed under different industrial conditions. Air warfare in the 1930s was evolving rapidly, and Japan saw the potential to convert a commercial airliner into a long-range bomber. A plane like the DC-4 could theoretically carry significant payloads over thousands of miles, bridging the Pacific and striking targets that were otherwise inaccessible. Japanese planners imagined a bomber that combined the comfort and range of an American airliner with the destructive capability of military ordnance. However, transforming a civilian aircraft into a military platform required more than copying dimensions and materials. Aerodynamic balances, engine performance under load, structural integrity under stress, and fuel efficiency all had to be recalculated. These were areas in which Japan's engineers were still developing expertise. The reverse engineering effort was ambitious but also risky. The Japanese team faced fundamental challenges, starting with the engines. The American aircraft used high-performance radial engines that had been optimized for weight, fuel efficiency, and reliability. Japan attempted to produce domestic equivalents, but limitations in metallurgy, manufacturing precision, and testing facilities created engines that could not match the originals. Early test runs revealed overheating, insufficient thrust, and mechanical failures. Despite careful study, the subtleties of American design, small adjustments to engine mounts, cooling systems, and propeller pitch proved difficult to reproduce. Beyond propulsion, control systems posed another significant challenge. The DC-4's responsive handling was the result of years of aerodynamic testing and refinement. Japanese engineers replicated the physical components, but without fully understanding how small adjustments influence flight behavior, the controls were often sluggish or unpredictable. Even the balance of the aircraft, which in the American design allowed for smooth and stable flight, was difficult to achieve. Weight distribution, fuel placement, and payload considerations became constant problems. Engineers discovered that simply duplicating the blueprint was not enough. Successful aircraft design depended on a deep understanding of the interplay between structure, aerodynamics, and engine performance. This period also highlighted the broader context of technological espionage. Japan was not unique in studying foreign aircraft. Nations across the globe had long observed and copied innovations, but the Japanese effort was particularly focused and state-driven. Military authorities believed that mastering American designs could shorten development time and give Japan a strategic advantage in the looming conflict across the Pacific. Every day that the reverse-engineered aircraft project continued, engineers faced the tension between ambition and the limits of replication. Their notebooks filled with measurements, sketches, and calculations, yet each discovery was shadowed by the realization that subtle details, those that might appear insignificant to an outsider, were critical to flight safety and performance. Despite the challenges, the project pressed on. Japanese engineers attempted modifications, hoping to correct weaknesses in the engines and controls while maintaining the overall design. They experimented with different metals, adjusted wing structures, and tried to reproduce the American airliner's interior layout for potential troop or cargo transport. Each test flight was closely monitored, and each failure provided lessons that, while frustrating, contributed to Japan's growing understanding of modern aircraft design. However, the distance between imitation and mastery remained wide. The meticulous craftsmanship and industrial integration achieved in the United States had been honed over decades, and it became increasingly clear that copying alone could not produce the same level of reliability and performance. By the early 1940s, Japan had created an aircraft that resembled the American design in appearance, but not in capability. The plane could take off, fly short distances, and carry a limited payload, yet it was fundamentally flawed. The engines were underpowered, the controls were awkward, and the airframe struggled under stress. This phase of experimentation demonstrated both the audacity and the limitations of reverse engineering. Ambition alone could not substitute for experience, precision, and an industrial ecosystem capable of supporting cutting-edge aviation technology. The story of Japan's espionage and reverse engineering effort offers a window into the complex intersection of ambition, technology, and international competition. While it was driven by strategic necessity, it also revealed the immense skill and knowledge embedded in American aircraft design. Each failure in Japan's project underscored the challenges of copying without comprehension and highlighted the gap between observation and true innovation. The lessons of this episode would resonate far beyond the immediate context of the war, illustrating the dangers of assuming that duplicating a design is equivalent to mastering it. In the early 1940s, after years of meticulous reverse engineering, Japanese engineers finally prepared their modified airliner for flight. The project had taken longer than anticipated, with each component scrutinized, tested, and reassembled in hopes of creating a plane that could serve as a long-range bomber. The ambition was immense, a single aircraft capable of crossing vast distances over the Pacific, delivering payloads that could influence the outcome of future conflicts. Yet, from the moment the plane left the ground, it became clear that imitation alone could not replace genuine innovation. The first test flights were tense affairs. Engineers and military observers crowded around the airfield, watching as the aircraft taxied, accelerated, and lifted from the runway. The engines, which had been painstakingly constructed to mimic the original American models, struggled under the load. On takeoff, the plane required nearly twice the runway distance of the original, and even then, the climb was slow and unsteady. Controls that were supposed to respond smoothly felt heavy and unresponsive, making the aircraft difficult to maneuver. Every landing became a cautious operation, with pilots fearing that a minor miscalculation could result in disaster. The problems were not limited to the engines and controls. The airframe itself revealed the consequences of Japan's assumptions. The engineers had replicated the dimensions and structure of the American design, but the materials and manufacturing processes available in Japan differed significantly from those used in the United States. Metals were prone to fatigue, welds were inconsistent, and the overall integrity of the fuselage and wings was compromised under stress. Engineers attempted modifications, reinforcing weak points and adjusting control surfaces, yet every change seemed to introduce new problems. The aircraft could fly, but it could not fly well, and it certainly could not carry the heavy loads that the military had envisioned. Air warfare had taught nations that long-range bombers required precise engineering, rigorous testing, and the ability to adapt to changing conditions. Japan's ambitious project demonstrated how a lack of comprehensive understanding could undermine even the most determined efforts. The designers had assumed that duplicating the appearance of a plane was sufficient to reproduce its performance. They had not fully grasped the subtleties of weight distribution, aerodynamic balance, or engine efficiency that were critical to the success of the original American design. As a result, the aircraft was fundamentally flawed, incapable of fulfilling the strategic missions for which it had been intended. Pilots who flew the aircraft reported numerous issues. Engine failures were common, particularly under full load, and the aircraft's sluggish controls made rapid maneuvers difficult. Even in calm weather, the plane required constant adjustments to maintain stable flight. Any attempt to simulate a combat scenario highlighted the limitations. The aircraft could not carry sufficient ordnance, it could not reach the distances projected in planning, and it was highly vulnerable to mechanical failure. Military planners recognized that the bomber, while impressive in appearance, was not operationally viable. The dream of a long-range aircraft capable of striking distant targets was, in reality, a fragile illusion. This failure illuminated a broader truth about innovation. The Douglas DC-3 and DC-4 were not merely machines. They were the result of a cumulative process of trial, error, and refinement. Engineers in the United States had spent years testing engines, adjusting wing shapes, balancing loads, and understanding the interactions between every component. Industrial capacity, skilled labor, and experience all contributed to the aircraft's success. Japan's engineers, by contrast, were attempting to leapfrog these processes by reverse engineering an existing design. Without the benefit of decades of accumulated knowledge, their efforts were inevitably constrained by gaps in understanding and technological limitations. The consequences extended beyond mechanical failure. The project consumed significant resources and manpower, diverting attention from other military priorities. Time, materials, and expertise that could have been used to develop indigenous designs were instead devoted to attempting to replicate a foreign aircraft. In the broader context of the war, the failure of the modified airliner symbolized the dangers of over-reliance on imitation and the risks of underestimating the complexity of advanced technology. The project became a cautionary tale within Japan's military-industrial establishment, highlighting the limits of copying without comprehension. Despite these setbacks, the Japanese engineers gained valuable lessons. They learned about American approaches to aerodynamics, engine design, and aircraft construction. The failures underscored the importance of rigorous testing, precise manufacturing, and iterative design processes. While the modified aircraft could never achieve operational status, the knowledge gleaned from its development would influence future Japanese projects, informing design decisions and highlighting the critical gaps that could not be bridged by replication alone. In retrospect, the ambition behind the project was both admirable and tragic. Japan sought to harness the most advanced American aviation technology and transform it into a military asset. The attempt revealed the limits of technological imitation and the dangers of assuming that outward appearance could substitute for expertise. The aircraft itself, though visually similar to its American counterpart, embodied the perils of hubris and the complexities of engineering mastery. It stood as a stark reminder that true innovation requires more than observation and replication. It demands understanding, experimentation, and the incremental accumulation of knowledge. The story of this modified plane illustrates a timeless lesson in engineering and history. Even the most determined effort cannot overcome the intricate knowledge, industrial capability, and meticulous testing embedded in a well-designed machine. Japan's ambition collided with reality, and the result was a project that failed to achieve its intended goals. Yet, in failure, there was insight. The experience reinforced the notion that technological supremacy is earned, not borrowed, and that the path from observation to mastery is neither simple nor short. In the annals of aviation history, this episode remains a vivid example of how ambition meets reality, and how the desire to emulate brilliance without understanding can lead to unforeseen consequences. In October 1941, as the Pacific Theater intensified, the story of Japan's modified airliner project reached its final chapter. The aircraft, which had been painstakingly reverse-engineered from American designs, never achieved operational status, yet its legacy offers profound insights into both engineering and history. The failure of the project underscores a critical lesson. Technological innovation is not merely about replication, but about deep understanding, iterative testing, and the integration of complex systems. The Japanese engineers had captured the shape of the aircraft, the arrangement of engines, and even the interior layout, but the subtle genius embedded in the original design remained elusive. Before the United States had perfected its long-range airliners, engineers had spent years refining every detail of the DC-3 and DC-4. Materials were carefully chosen for strength, weight, and reliability. Engine components were designed for optimal performance across a wide range of conditions. Aerodynamic calculations were tested repeatedly in wind tunnels, and control systems were adjusted to ensure predictable and responsive handling. Every successful flight was the result of accumulated knowledge, rigorous experimentation, and incremental improvements, a process that could not be hurried or superficially copied. The Japanese project highlighted the gap between imitation and innovation, showing that even a visually identical aircraft could fail spectacularly if the underlying engineering principles were not fully understood. The practical consequences of the failed aircraft were significant. Japan had invested substantial resources into the reverse engineering program, including labor, materials, and technical expertise that could have been applied to indigenous designs. Every flight test revealed additional shortcomings, from underpowered engines to poor handling and structural weaknesses. The military potential of the aircraft was limited. It could not carry the intended payloads over the desired distances, and its operational reliability was far below the standards required for combat missions. Despite the engineers' best efforts, the project never produced a usable long-range bomber, and its existence became a cautionary tale within Japan's aviation circles. Yet the story is not solely one of failure. In attempting to replicate American technology, Japanese engineers gained exposure to advanced design concepts, manufacturing techniques, and aerodynamic strategies. They learned about weight distribution, structural reinforcement, and engine performance under stress. These lessons, although gleaned through trial and error, contributed to Japan's broader understanding of modern aircraft engineering. The experience reinforced the importance of testing, adaptation, and respect for the complexity of technological systems. It illustrated that mastery of technology requires not only observation, but also sustained experimentation, critical thinking, and the ability to innovate when existing solutions fall short. The episode also highlights the broader historical context of innovation and espionage. During the 1930s and 1940s, nations across the globe recognized that technological supremacy determined military outcomes. Aircraft design, in particular, became a focal point for both legitimate research and covert observation. Japan's project demonstrates how ambitious nations sought to shortcut the development process by copying proven designs, yet it also reveals the inherent limitations of this approach. The story of the modified airliner stands as a vivid illustration of the tension between ambition and technical reality, between aspiration and capability, and between imitation and true invention. Meanwhile, in the United States, the DC-3 and DC-4 continue to shape the future of commercial aviation. The DC-4, with its four engines, long range, and reliable performance, became a cornerstone of wartime and post-war transport. Airlines expanded routes, cargo could be delivered over unprecedented distances, and the aircraft proved its versatility in both civilian and military contexts. The contrast between the American success and the Japanese failure underscores the role of comprehensive industrial infrastructure, skilled labor, and accumulated engineering expertise in achieving technological breakthroughs. It is a reminder that true innovation is rarely instantaneous. It is earned through persistence, precision, and an understanding of the interplay between materials, mechanics, and aerodynamics. From an educational perspective, the story offers a compelling lesson in the human dimensions of engineering. The Japanese project was driven by ambition, ingenuity, and determination, yet these qualities alone could not compensate for gaps in knowledge and experience. It emphasizes the importance of problem-solving, adaptation, and critical analysis, qualities that engineers, historians, and innovators must cultivate. It also serves as a cautionary tale about the limits of copying and the potential consequences of underestimating the complexity of technological systems. Success in engineering is not merely about producing something that looks like an original. It is about achieving functionality, reliability, and safety, all of which require deep comprehension and careful execution. Ultimately, the story of Japan's attempt to reverse engineer American airliners bridges history, technology, and human ambition. It illustrates the dangers of hubris, the value of incremental progress, and the extraordinary effort behind aviation achievements. While the aircraft itself never fulfilled its intended mission, its development provides insight into the broader narrative of innovation, competition, and learning from failure. The Japanese project reminds us that the history of technology is shaped as much by lessons learned from setbacks as by triumphs, and that the path to mastery is paved with both observation and original thought. Today, when we look at the legacy of the DC-3 and DC-4, we recognize more than just engineering excellence. We see the culmination of dedication, creativity, and rigorous testing that produced aircraft capable of reshaping both civilian and military aviation. In contrast, the story of the Japanese reverse-engineered plane endures as a testament to the limitations of imitation and the importance of cultivating true understanding. It is a story that continues to educate, inspire, and remind us that ambition, no matter how bold, must be paired with expertise and insight to achieve enduring success.